Hi, this is Pat Kaplo. I'm solving problem number 18 in the Giancoli textbook. On page 188, it reads, "You are the design engineer in charge of the crash worthiness of new automobile models. Cars are tested by smashing them into fixed, massive barriers at 50 kilometers per hour. A new model of mass 1,500 kilograms takes 0.15 seconds from the time of impact until it is brought to rest. A. Calculate the average force exerted on the car by the barrier, and B. Calculate the average deceleration of the car." I've made a quick sketch. You can see that a car is approaching a large concrete barrier. That concrete barrier is fixed. It's not going to move. Let's go ahead and start writing our initial conditions. We know that the mass of the car is 1,500 kilometers. We also know that the initial velocity of the car is given to us in the problem at 50 kilometers per hour. 50 kilometers per hour should immediately recognize that unit right there is not appropriate for solving problems using any of the equations and concepts we've talked about. So it would be important, of course, to quickly convert that to meters per second. In this case, divided by 3.6, which is the conversion factor. You'll end up getting 13.9 meters per second being the velocity of the car before impact. The implication is that the velocity of the car after impact is 0. So I could adjust this subscript and say that the velocity v naught before impact is 50 and v final after impact is 0 meters per second. The car is brought to rest. You're given the time of impact, 0.15 seconds or 150 milliseconds is the time of impact. And the question then is, what is the average force exerted by the car? That's the question in Part A. Part B is asking for the average acceleration or deceleration during that period. One thing that we have talked about in class is any question that typically is asking for time or force is going to fall under a category of momentum problems where you're applying the impulse momentum theorem. In its most general form, impulse momentum can be written as Ft equals delta P, or force times a time interval, which we call impulse, is equal to a change in the object's momentum. Further expanding the term on the right, I can say that force times time is equal to the final momentum minus the initial momentum, or I can say m delta v, where the mass of the object doesn't change, but more importantly, its velocity does here in this particular case on the right. That's the form of the equation I'm going to choose to start with, and I'm basically solving for this term here, average force, the one on the left-hand side. So I can say that the average force is equal to m times delta v divided by the time interval will yield the average force during the collision. Force, now I'm just substituting. I have all of these variables. 1,500 kilometers. Oops, 1,500. I'm sorry, not kilometers. 1,500 kilograms times the change in velocity. This gets a little tricky. It's important to keep here in mind that the final velocity is 0 and the initial velocity is 13.9. So technically speaking, I could rewrite this term here, change in velocity, as v final minus v initial, or 0 minus 13.9 meters per second. Of course, that's going to yield a negative sign, which is going to tell me that the direction of my average force is to the left. I'm going to divide that by the time of impact, or 0.15 seconds. I'm now left with my average force as 138,890 newtons, which of course I'm going to have to deal with significance, so I'll leave that as 140 kilonewtons or 140,000 newtons, whatever you're more comfortable with. That's the average force. It's important to keep in mind this concept of average force. Over in the bottom left-hand corner, I'll just make a quick graph, perhaps, of force versus time profile, where my x-axis is time in seconds, and my y-axis is force measured in newtons. In the real world, you're seldom going to get a curve, or I should say a nice, yikes, a nice even shape like this. So your force time profile generally doesn't look like that, and what generally you see is curves. The area under a curve is important. That's, of course, the impulse. It's the force times the time. In mathematics, the area under the curve is known as the integral. This particular curve would have a function, f of x, and would be integrating the function between the lower limit here and the upper limit here. That's a bit beyond what we're studying in this class, applying those elements of calculus. I think you need to recognize that we are solving for this average force that occurs. It's important to see here that there is a peak force that could occur that is larger than the average force that we found. We're in effect simplifying our answer and just saying that the average force during the collision is 140,000 newtons, although it could be much more at an instantaneous point in time. Part B of the problem asks us to further solve for the acceleration experienced by the car, or potentially the driver, I suppose, during that event. Part B of the problem is quite straightforward. I'll do it on a separate sheet here. For part B of the problem, we can simply say that we can apply Newton's second law, F net equals ma, and we're solving for the acceleration of the car. We know the net force applied to the car. We've solved for that in the previous problem, and now we just rearrange. So acceleration is equal to our net force divided by the mass of the car, and we can now say, and I'm going to use the 138,890 Newton figure that I solved for before I truncated for significance, and divide by the mass of the car. The 1,500 kilograms is going to be equal to my acceleration. And I'm going to get something on the order of 92 meters per second squared here is equal to my acceleration. So I'm getting something pretty substantial here if you kind of convert that into g's by dividing by 9.8, which is kind of be your standard of comparison. You're going to get something on the order of about 9.4 g's, which is substantial. Not necessarily survivable, but possibly. Depends, I think, on other circumstances. So the answer to part B then would be this figure, since they didn't ask to convert it into g's.